Is that okay? All right. So on the side, I'm going to use mouse pad. I think I might have one open already. Yep. And we'll go ahead and play out a few scenarios and find out what's going to happen when x is low and y is low as well. Okay, so we want to look at this particular scenario. Let me turn off line number because we don't need it in this case. What's going to happen? So we'll go ahead and take a look at the transistors first. Okay, so the first thing we want to know is, are we turning on or turning off, all of these transistors? So we'll go ahead and list Q1 all the way to Q4. So is Q1 on or off when X is low, Y is low? There's a bubble, which means a high voltage is going to turn it off, which means a low voltage is going to turn it on. Okay, so Q1 is on. What about Q2? On. Q3 and Q4 is off. Okay, very good. Okay, so not talking about device physics. When you look at the output pin, which is the bubble, all the way to the right-hand side, where is it connected to? We know Q1 is on, which means it is connecting. We know Q2 is on, which is also connecting. So when you look at this output pin, it is actually connected to this triangle pointing up, which is high voltage. Is that making any sense? Yep.
How does it flow? Does it go first horizontally, then downward, or does it just go both directions?
Well, logically, it is just connecting. In other words, okay, flow is very confusing in this case because we also have the confusion of current versus the direction of electrons. Okay, when you look at current always goes from positive to negative. But when you look at electrons, which is a negative charge, it always goes from a negative source to a positive source. Okay, so in this case, all we really need to know is this is connecting, and since this is connected to here, now logically it is connected to the high voltage source, which is represented by the arrow pointing up. So the actual physical thing can be confusing, so I try to avoid using the actual physical flow. Yep.
So would the ground be negative? Would the ground
yes. So the ground is technically 0, but it is lower than the positive voltage. Okay. So with all of this, the output is connecting to the high voltage. Is that okay? Because this symbol is representing a high voltage, this symbol is representing 0 volt or low voltage. Are we doing okay so far with this? Okay. So we're going to look at another scenario and say X is high, Y is low. Okay, so this one is a little bit more interesting because things are no longer symmetric. So we'll look at the 4 transistors. So we know X is a high voltage. So X connects to Q1. So what is that going to do to Q1? Q1 has a bubble at the gate. It's going to turn it off, right? So Q1 is off. All right. What about Q2? Q2 connects to Y. Y is low. There's a bubble here, which means it's on. Okay, very good. What about Q3? Q3 is on because there's no bubble here, and X has a high voltage. So high voltage at the gate turns it on, and then Q4 is off because it is an N transistor, and we have a low voltage because it connects to input Y. Are we doing okay so far with the analysis of the state of the transistors? Now remember, a transistor is a valve. Okay, it is either allowing flow when it's on, or it is cutting off flow when it is off. Okay, so let's take a look at this picture here. Q1 is off, which means this point and this point are now disconnected if you just look at this part of the picture. But Q2 is on, which means this is connecting. What about Q3 and Q4? Q3 is on, but Q4 is off. Now the trick here is Q3 and Q4 are connected in series, but Q1 and Q2 are connected in parallel. So when you have something that is, when you have two things or two valves that are connected in series, if one of them is off, it's cut off. If at least one valve in series is off, the entire chain is off. Is that making any sense? But on the other hand, Q1 and Q2 are connected in parallel, which means you have two alternative paths to connect to the high voltage. If at least one of them is on, it's connecting. Is that making any sense? Okay. So what do you think would be the output of this particular case?
High.
Yep, the output is a high. Okay. So you can work out all 4 possible scenarios. Now, how come there are only 4 possible scenarios?
There's 2 settings per meter.
We have 2 inputs, and then each input can either be a low or high, or 2 choices. So we have 2 to the power of 2 possible ways to configure the inputs. So there are 4 scenarios to play out. I'll let you guys play that out also. But the bottom line is the result can be represented using well, these are the scenarios. But the bottom line is there are 4 possible ways to look at how the input XY relates to the output pin. A 0 is a low voltage, a 1 is a high voltage. Instead of writing HI high and elbow low, I just use 0s and 1s in this case. Is that okay? All right. Okay. So there are these 4 possible scenarios. By working out the states of each valve and also how they are connected in the circuit. So when you look at this, you go like, okay, well, what about it? It seems like it resembles one of the logical operators that we are familiar with, because the only time that it is different from the other 3 times is when X and Y are both 1s, then the output is a 0, but for all of the other ones, the output is a 1. So it's kind of like AND, right? Because when you look at logical AND, the only time that you get a 1 out of a logical AND is when both inputs are true. All of the other cases will end with false. This is almost like that, except it's flipped. Is that making any sense? So when you're expecting the result to be a 1 using an AND, this one is false. When you're expecting the result to be false using a regular AND, these are trues. So we have a negated AND gate. It is almost just like an AND gate, except there's a negation in front of it. So the symbolic way to look at this, so if we look at the output as W, then W is, this is using C syntax, by the way. So W is exclamation point X and Y. So it's a negated AND. Is that okay? I'm running out of time. Okay, so I will make this material available to you as soon as I can. Oh, we have a lab after this, so I can actually continue. I can keep running, in the lab. So, but the point is, this is the mathematical symbol. So what is so special about the negation of AND? It's just some weird way of using the logical operators, right? Well, as it turns out, it is the only operator that you will need. In other words, if negated AND is available as a single operator in C and C++, you will not need the other operators at all. If NAND is available, you would not need AND. You would not need OR. You would not need negation itself. This is the one operator. This is the one ring that can rule them all. Okay? This is the one operator that can operate all. Okay? Really? And you go like, how? How is that possible? Well, as it turns out, you can re-express negation using X NAND X. You can re-express X and Y as X NAND Y NAND X NAND Y. And you can re-express X or Y as scroll as X NAND X NAND Y NAND Y. So that one single operator can replace, well, with some tedium, all of the other operators. Okay, so we are moving on to the lab because I want to show you, tech, you can talk about this all day long, but I would like to have some hands-on experience. I want to play with these transistors and play with the input and see for myself that it operates the way they're supposed to operate. Okay, so in the lab session, which is in 126, I'm going to show you guys how to do it. And that's the tool that we'll be using for the entire semester. Okay, so that means if you attend the lab session, you'll be learning something that will be useful for the rest of the entire semester. And it's really fun to use too. So I'll see you guys in a few minutes in room 126. And that portion will be recorded as well.